In this final example, we'll show that you can have a function which is infinitely differentiable at some point, so that you can define Taylor series for this function centered at that point. And yet, the sum of a Taylor series is not going to be equal to the function itself anywhere except for the center of a series. So let's define f of x to be the following. It's going to be e to the power minus 1 over absolute value of x if x is not equal to 0. And it's going to be 0 if x is equal to 0. And what I want to construct is the Taylor series for this f of x. Taylor series again centered at 0 because we're talking about just that, Taylor series centered at 0. Okay, so when can I construct a Taylor series? I can do that as long as my function is differentiable infinitely many times at 0. And if I look at this f of x, and clearly it is differentiable if x is not equal to 0, right? Because if x is not equal to 0, then exponential function is differentiable. And if you're away from 0, then absolute value of x is a differentiable function as well. So composition of two differentiable functions, everywhere differentiable functions, is going to be differentiable. Okay, so, but in this case, if I want to compute a derivative at 0, I cannot really be sure that that derivative exists unless I'm able to compute it, right? Because the exponential function, or rather minus 1 over x, absolute value of x, is not defined at 0. So it's not clear if f is going to be differentiable. So the only recourse here is to try to compute a derivative at 0 and see what it is. Okay, so if I want to compute a derivative at 0, then what should it be? By definition of a derivative, f prime of 0 is a limit x goes to 0 of your function f of x minus same function evaluated at 0 over x minus 0. So in this case, f of 0 is 0, so this is just a limit x goes to 0 of f of x over x. All right. One thing that I know about this function is that this function should be even, right? Because it depends on absolute value of x. So if I plug in minus x into the function, I'm going to get the same value as at x. So the graph is symmetric with respect to the y-axis. And so then if I want to take a derivative at 0, right, because I'm dealing with an expression that involves absolute value of x, I can try to compute a derivative from the left and then right, and from the right, and see if those two match. And really, I can only take one derivative from the right, because derivative from the left is going to be the same thing, but multiplied by the minus sign. So let's take a limit as x goes to 0 plus of f of x over x first, and then we will extrapolate to the limit from the left. So what is that? That's a limit x goes to 0 plus of, so now exponential e to the minus 1 over absolute value of x. I can drop absolute value sign because x is positive, so you'll get e to the minus 1 over x divided by x. All right, so we have this. Now, what is this limit? If I look at it carefully, right, so x goes to 0, then denominator, of course, goes to 0. But also if x goes to 0, then 1 over x goes to plus infinity. X goes to 0 plus, right, from the right. So 1 over x goes to infinity, e to the power minus 1 over x then goes to 0. And so what I got is an indeterminate form, 0 over 0. Well, so then one thing that I can try to compute this limit is L'Hopital's rule. So if I try to use L'Hopital's rule here, let's see what we will get. So by L'Hopital's, this is the same thing as the limit x goes to 0 plus. Denominator is simple, right? Its derivative is equal to 1. And derivative of the exponential is itself, e to the minus 1 over x times derivative of minus 1 over x, and that's 1 over x squared, right? So it's minus x to the minus 1, take a derivative, minus 1 comes down, becomes 1, and then you have to increment the derivative or decrease the power of x by 1, so you get x to the minus 2, which is the same thing as the limit x goes to 0 plus e to the minus 1 over x squared. Well, so have we achieved anything good here? No, because we started with e to the minus 1 over x, and we ended up with e to the minus 1 over x divided by x squared, right? So this is certainly not better or easier to compute because this is still in the determinant form. And that means that if I continue using L'Hopital's rule, I'm going to only increase the power of x in the denominator, and so that's not going to be of any use to me. So we have to be a little smarter here. And one way to proceed is going to be as follows. So again, so that's not working here. So let's try this. What if I denote by y 1 over x? So I'm going to set y to be 1 over x. Then if x goes to 0 plus, this would be the same thing as saying y goes to infinity. And therefore, I can write my limit. So limit x goes to 0 plus e to the minus 1 over x, I can write as a limit x goes to, not x goes to, but y goes to infinity of e to the power minus y. And then what about what about x? X is 1, if y is 1 over x is 1 over y, so we have e to the minus y, and we're dividing it by 1 over y, right? And so that becomes the limit y goes to infinity. Dividing by 1 over y is the same thing as multiplying by y, so we have that. And e to the minus y I can move to the denominator, so I'm getting a limit as y goes to infinity, y over e to the y. All these manipulations, what do they bring me? So now I have y goes to infinity, so numerator goes to infinity, and e to the y, that also goes to infinity, right, as y goes to infinity. So instead of having a limit 0 over 0, I have a limit infinity over infinity. And I can try to use L'Hopital's rule here. And if I do this, then what am I going to get? I'm going to get a limit as y approaches infinity of 1 over e to the y, right? Because now I'm taking derivatives with respect to y. And of course that is equal to 0. And so by doing this trick, and then using L'Hopital's rule, I can find what the limit is. So it is 0. And so therefore, this limit is 0. And now we're going to use the symmetry of f of x to compute the limit from the left. So if I take a limit x goes to 0 minus of f of x minus f of 0 over x minus 0, what should that be? So this is still limit x goes to 0 minus. In the denominator I have simply x again, right, because x minus 0 is 0. F of 0 is still 0. And now f of x at minus x, so at minus x, absolute value of x is still positive. So to get absolute value of x from x, I have to multiply x by minus 1. So we have e to the minus 1 over minus x, so that's just e to the 1 over x. So e to the 1 over x. Then, again, I'm going to change a variable. So if x goes to 0 minus, let's change x to t and call t equal to minus x. So in this case, if my variable is t instead of x goes to 0 minus, then t will be reflected and go to 0 from the right. E to the minus 1 over t, and then minus t in the denominator. I can pull the minus sign in the denominator out of a limit, so that's minus a limit t goes to 0 plus e to the minus 1 over t. But then that limit is exactly the same as the limit that we just computed, except that it's written using a variable t, but otherwise it's exactly the same thing. So this should be 0 as well. And so now we have a limit from the left is 0, limit from the right is 0, and so therefore a limit x goes to 0 of f of x minus f of 0 equal divided by x minus 0, which actually is the definition of a derivative of f, right? That is equal to 0. Okay? All right, so that means that our function is differentiable at 0, and the derivative of x at 0, not at x, oops, derivative of f at 0 is equal to 0. And so now we can actually write down the expression for f prime of x everywhere. So f prime of x is going to be I also need to figure out how to take a derivative when x is not 0, right? But then again, I have a recipe there, and the recipe is a differentiable function. If x is positive, let me move this down a bit. So also, if x is greater than 0, then f prime of x is a derivative of e to the power minus 1 over x, right? And that should be, again, the exponential itself times the derivative of minus 1 over x, which is 1 over x squared. And if x is less than 0, and then the derivative is, if x is less than 0, then absolute value of x is minus x. So again, this is e to the 1 over x prime, and derivative of that is minus e to the minus 1, e to the 1 of, sorry, minus e to the 1 over x times the derivative of 1 over x, which is minus 1 over x squared. And so we have 3 different prescriptions now. So if you compute f prime of x, if x is negative, then f prime of x is minus e to the 1 over x squared. That is if x is less than 0. If x is equal to 0, then derivative is 0. And if x is greater than 0, then the derivative is going to be e to the minus 1 over x squared if x is positive. All right, so then f prime of x is defined everywhere for all x, negative, positive, and 0. And of course, when x is negative or x is positive, f prime of x itself is a differentiable function, right? So if x is negative, then I can compute f double prime of x. And that's going to be a derivative up here, which I can compute by using the quotient rule and the chain rule. So derivative of, I still have minus sign in front. Derivative of a top is derivative of e to the 1 over x, so that's e to the 1 over x times minus 1 over x squared times the bottom, which is x squared minus the top times derivative of the bottom, that is 2x. And then denominator is the bottom square, so that should be x to the 4th. And we actually can simplify this a little bit. X squared cancels out. And then the minus signs I can pull out, and they will cancel with minus sign up here. And e to the 1 over x I can factor out. And so if I do all of this, I'm going to end up with 2x plus 1 times e to the 1 over x divided by x to the fourth. Right? So if x is positive, I can compute the second derivative. If x is negative, I can also compute the second derivative. So if x is negative, I can compute the second derivative. If x is positive, I can do the same thing. Then f double prime of x is going to be the derivative of this guy. And a similar procedure will work. Take the derivative of e to the minus 1 over x, that's e to the minus 1 over x times 1 over x squared, multiply by the denominator by x squared, subtract e to the minus 1 over x times the derivative of the denominator, which is 2x, and then divide by x to the fourth. And so if I then do the similar thing here and simplify this expression, x squared once again cancels out. And so I'm going to get 1 minus 2x times e to the 1 over x to the fourth. Now let me just double check something here. E to the minus 1 over x. Okay, so the derivative is differentiable both if x is positive and negative. And so the only question is whether or not the derivative is going to be differentiable when x is equal to 0. So let's look at x equal to 0. Again, f double prime of x, f double prime of 0 is the limit x goes to 0 of f of x, f prime of x, minus f prime of 0 because it's the derivative of f prime, divided by x minus 0. But I already determined that at x equal to 0, derivative is 0. So this thing will drop out, and x minus 0 will be just x. And so that is a limit x approaches 0 of f prime of x over x. And again, I can compute this limit by taking a limit from the left and the limit from the right and making sure that these limits are the same. So let's take limit x goes to 0 plus of f prime of x over x. What is that? What's f prime of x when x is positive? It's going to be this expression. So it's a limit x to 0 plus e to the minus 1 over x squared, and then I'm also dividing by x, so this should be x cubed. And then I can use the same trick as I used before, y equal to 1 over x. And if y is equal to 1 over x is 1 over y. And my limit becomes, limit now y goes to infinity, e to the minus y, and x is 1 over y, so 1 over y quantity cubed. So then y goes to the numerator, e to the minus y becomes e to the y in the denominator, so limit y goes to infinity, y cubed over e to the y. And then if I use L'Hopital's rule on this, derivative of the denominator is exactly the same, right? Because again, I have to use L'Hopital's rule because it's an indeterminate form, infinity over infinity. If I use L'Hopital rules on the bottom, I get e to the y again. Use L'Hopital's rule on the top, you get 3y squared. This is still infinity over infinity, but you reduced the power of y in the denominator. So if I use L'Hopital's rule, 3 times? And then this becomes a limit y goes to infinity of 6 third derivative of y cubed over e to the y, and so that is 0. Now we take the same limit, but from the left, x goes to 0 minus, and in that case, f prime of x is that expression here. So limit x goes to 0 minus of minus e to the 1 over x divided by x squared, right? And there is an additional x that we have in the denominator here, so divided by x cubed. And then I'm simply going to relate it again to the limit from the right by writing t is equal to minus x. So then x is minus t. And this is a limit t goes to 0 plus, right? Because if we're using t, we reflect it with respect to the origin. And then e to the, or minus e to minus 1 over t. And of course, minus t cubed in the denominator. So then minuses will cancel each other out, right? Because minus cube is minus 1 cube is a minus. So minuses cancel each other out, and this is a limit as t goes to 0 plus of e to the minus 1 over t cubed. And that we already computed up here, and we know that this is equal to 0. And so therefore just a limit as t goes to 0, e to the minus 1, let's see of what, not e to the minus 1 over t, but f of x, f prime of x minus f prime of 0, x minus 0, that this is 0. And that limit, of course, is once again f double prime of 0, so we show that f double prime of 0 is equal to 0. All right, so now I'm going to write dot, dot, dot. You can check the book for additional details of the next step, but then by using induction, we can show that fn of 0 is equal to 0 for any n and n. Right, so that the function that we defined, even though it is a piecewise defined, it ends up being differentiable infinitely many times at 0, and all derivatives of that function, in fact, are equal to 0. Okay, fine. And so if then that is the case for the function which is differentiable infinitely many times, I can compute a Taylor series, And the Taylor series is, again, sum from 0 to infinity f nth at 0 over n factorial times x to the n. But in this case, f nth of 0 is always 0. And the function itself at 0 is equal to 0. So this is 0 for all x, because all coefficients are equal to 0. But then this is, so therefore, sum from 0 to infinity of f nth of 0 over n factorial x to the n is equal to our f of x only at x equals 0 and nowhere else. And so that means that actually the function is not going to be equal to, right, because f of x is not 0 anywhere else. It's an exponential function e to the minus 1 over x at all other points, and that value is not equal to 0. And so that means that the information about this function at 0, right, all derivatives of this function at 0, do not really carry in themselves any information about what the function is doing, the function f of x is doing nearby, right? Because if the function is equal to the sum of its Taylor series, then clearly the Taylor series only depends on the function and its derivatives at x equal to 0, right? Because coefficients are defined as values of the derivatives at 0. So it means that what the function does at 0 determines what it is doing nearby. But apparently this only works for some very special functions, not for all functions. For functions like the one that we're just considered in this example, clearly the fact that the function and its derivatives at 0 are equal to 0 doesn't tell us anything about what the function is doing at any point inside in the vicinity of x equal to 0 or anywhere else for that matter. Okay, and so that is the last thing that I was going to say about differentiation, and then next time we're going to start discussing integration.